We're going to do something a little bit different today. We're not going to get very far. We're probably going to go, well, we're just going to go through radioisotopes. We'll save radioactive half-life for, today's Friday, so that'll be Wednesday. So what I want to do today is, generally I try to review what it is that we did the class before. So we'll talk about what it is we did then, and then we'll press on into atomic nomenclature and talk about radioactive isotopes, or we'll talk about isotopes, isomers, and all that. But we'll spend a little bit of time reviewing, pressing on into the other information, and then what I want to do is I want to bring up the review and show you how to use the review, and kind of explain what it is that when I lecture, where I'm coming from, so that maybe it'll help you to, when you're studying the review, to understand why it is I go in directions that may seem like they just don't matter. And sometimes they don't, to be completely honest with you, but most of what I say has eventually some sort of application to what we're either doing now or what we're gonna be doing in subsequent chapters. So they're not always rabbit holes for the sake of rabbit holes, but they are rabbit holes most of the time that lead to something that you're gonna need to know eventually. So what we talked about on Friday of last week was, the development of the atomic theory as it mainly pertains to what we do in radiology. So we talked about the different generations of the atom. We talked about I got to turn the air down in here again. Y'all got it like 90 degrees in here.
It's not working.
What's that?
I turned it on, but it's not.
It's not. I think you're just telling me that,
I
so I
did.
won't go back here and turn it down.
No, it's not.
Uh-huh.
Did
Uh-huh.
not?
Yeah.
Maybe somebody turned it back up.
You just started trying to burn me up. That's what it is. All right, so we talked about the Greeks defining what an atom was, and that was the smallest part of something that you could divide it out and still have that something. So the definition of the word means uncut, and that's exactly what it means, is that if you cut it down any further, it becomes something entirely different. And we looked at the water, even though water is not an atom, we looked at water as an example. You take one single piece of water and you cut it down, one molecule of water, and it becomes hydrogen and oxygen. So it's two totally different things, right? So we talked about the Greeks having their substances and essences. It really doesn't have a whole lot to do with us. But Mendeleev developed the atomic, the elemental table. And now we recognize 118 elements. And we're going to talk next week about man-made elements, the significance of man-made elements versus natural elements. So some of those are naturally found elements, and some are actually man-made. We talked about the Dalton atom, and the Dalton atom, the significance of the Dalton atom is that it introduced us to the concept of combining atoms to create something a little bit different. So we know that water is hydrogen and oxygen, so you got the hooks and the eyes that combine those two things together so that we create something that behaves a little bit differently than what the individual things behave as on their own. So we got two gases that come together to create a liquid. So he gave us hooks and eyes. The Thomson atom, the significance of the Thomson atom is kind of transient. It gave us the concept that the atom was made of different individual parts. So you had a well-defined nucleus, looked like a pudding, and you had the pudding, and then you had on the outside of the pudding, you had the electrons. So it gave us electrons, the concept that we've got a nucleus and we've got electrons. And then Bohr atom is the one that looks like a solar system. So the significant takeaways from the Bohr atom, and we're going to dial that in just a little bit more here in a bit, is that it kind of looks like a solar system. So you've got a well-defined nucleus that in our solar system analogy, that would be the sun, and the electrons would be the planets that buzz around the outside of the nucleus. So then we also talked about subatomic particles, and there's a lot of them, but we're only going to focus on 3. So, you know, if you go on a Google search and you look for subatomic particles and you look up quarks and you start studying all that, you're adding penguins you don't need, right? So 3, that is the proton, the neutron, and the electron, right? So you got those 3. And so in the Bohr atom, where we see the proton and the neutron is inside the nucleus. So how you identify each one of those is the proton is inside the nucleus, and we're going to talk a little bit more about each one of those particles here in a bit. But the proton's inside the nucleus, it's got a positive charge, right? The neutron is also inside the nucleus, and it's got a neutral charge. And remember, I said that you need to be thinking about the neutron as not being neutral by virtue of not having a charge at all, but rather it's neutral because it's got both charges. And we'll talk about that when we get into radioactive decay next week. And then the electrons are on the outside, and it's a negative charge. So the mass of the atom is inside the nucleus. If you remember, we've got atomic mass number, and the atomic mass number is just a rounded off atomic mass. And we assign 1 for the proton, 1 for the neutron, and 0 for the electron. So if the electron is so small that we don't give it any mass, then naturally, even if we combine all the zeros, you add 100 zeros, what do you have? 0, right. So even if we combine all those electrons, they're not going to add up to enough mass to really count. So the mass, the actual mass, is inside the nucleus. That's in the proton and the neutron. So the mass of the atom is found inside of the nucleus. The area of the nucleus, or I'm sorry, the area of the atom is, again, like our solar system, it's mainly empty, right? So 2 things to keep in mind there. So 3 fundamental particles, 2 in the nucleus, and they're in our solar system analogy. They are the sun, and the planets are the electrons that go around the outside. Protons positive, neutrons neutral, and the electron is negative. Same charge as the proton, it's just opposite, even though the sizes are so much different. 1 electron, 1 proton, you got a neutral atom. Okay. So we just talked about the atomic mass. Atomic mass number is a rounded version of the atomic mass unit. And that's all you need to know about atomic mass unit. Don't memorize the actual atomic mass unit. It's the actual weight of the subatomic particle. But we're going to use the atomic mass number just because it's easier, right? So the electron arrangement, we talked about the electron arrangement and how they're inside the shells in orbit around the nucleus of the atom. And we talked about how you could calculate the number of electrons that you're going to have in the shells, right? So we talked about 2 things in that. One is that you can calculate the number of electrons in any shell using a formula, and that formula was 2n squared, right? And then we talked about the outermost shell. 2 things about that. One is that if at all possible, your atom wants to have 8 in its outer shell. If it can have 8, then it's happiest. Obviously, that can't happen if you don't have 8 protons. Hydrogen has 1 proton. If you had 8 electrons in the outermost shell, then you'd have to have 2 shells, and it would be a highly charged particle, right? And it's just not a stable condition for the hydrogen atom to be in. But if at all possible, it wants to have 8 in its outer shell, and it can never have more than 8 in its outer shell. Okay, so I'm gonna pause there. I'll start talking about test-taking technique for a second, okay? So when you're taking your tests, I find it most helpful to take your Scantron. You've got your test. Take your Scantron, cover up your answers. Okay, read the question, understand what the question is saying before you look at your answers. okay? Because this is a test that people start to struggle a little bit in this class. So cover up your answers. Don't look at your answers until you understand the question. And then try to think of the answer before you look at your answers, okay? Once you've got your answer in your head, move your Scantron and see if your answer is in the list of answers, A, B, C, or D. If it's not there, then chances are you misunderstood the question, or, you know, I did like on this last test, I didn't fix my answers before, you know, gave the test. All right, so then if your answer is not there, then you go back up and you reread the question. If your answer is there, then overwhelmingly the odds are that's the right answer, right? So you answer the question, and then what do you not do?
Second guess yourself.
Second guess. Leave it alone. You know, don't second guess yourself. Don't erase it and go with something else. Leave it alone. Go to the next question. Don't overthink it. Okay. If your answer is there, then have at it. So that's one thing. Another thing is if you have a true-false question. Okay, a lot of people get tripped up on true-false questions whenever there are compounding and conflicting issues. Okay, so for example, you know, I make a dot on the board like that, and I make a true or false question. I say the dot is, make believe this is truly circular, is circular and green. What's your answer there?
False.
False, right. So the entire statement has to be true. If any part of the statement is false, then the whole statement is false. Right. So, you know, keep that in mind. Another thing is that if I say something like 2 or 3 times, like in a row, if I say something 2 or 3 times in a row, if I say something 2 or 3 times in a row, chances are that's on the test. And if I give you that answer and I say something following that, like I just answered that for you, I hope you were paying attention. What does that tell you?
It's on the test.
It's on the test, and I just gave you the answer, right? That's a rarity. I don't do that very often, but usually when I do that, it's because, you know, there's a specific question that students shouldn't miss, but do miss on a fairly regular basis. Okay, so you know that's your cue to pay attention in class, because if I do that and then you miss it, it's just like, come on, you know, you just weren't paying attention. All right, so and the other thing is that a lot of people get tripped up on some but not all the above, you know, some people, if there isn't an all the above, they're gonna pick it 100% of the time, right? And that's just not gonna apply here. You know, a lot of times when I give you an all the above, it's because I can't think of a fourth thing. In all honesty, I can't think of a fourth thing, and so it's just all the above. Okay, so if I were to give you a question like, well, we just talked about electron arrangement. If I were to give you a question that said, you can calculate how many electrons you can have in any given shell with, what would your immediate thought go to? 2 n squared, right. So what if one of the answers was 8 in the outer shell? What did the question ask you?
How to calculate?
How to calculate in
shell.
any given shell. Did I ask you about the outer shell? No, so don't read anything into it. I just gave you the answer to that question. Okay. All right. So, you know, you got to pay attention in class. You got to apply what you know. You got to not overthink, but you have to, and we're going to spend some time today kind of going through critical thinking. Okay, I want to preface this with saying my sister is a retired elementary school teacher. My daughter is a current elementary school teacher. My niece is a current elementary school teacher. I'm not beating on teachers. I'm beating on electors and on school administrators to teach tests. Okay, so they've done you no favors by getting you here by teaching a test. We don't do that here. You have to understand the concepts, right? Because I'm not going to write your registry. Somebody else, you know, they're going to take questions submitted by a lot of different people to write your registry. If I just get you to pass my tests and suddenly you get to somebody else's test questions, you're going to be in trouble, right? So you have to understand the concepts. So the purpose for the rabbit trails that are run down sometimes are to try to help you to understand those concepts rather than just understand. I can write an easy test. The easiest thing in the world for me to do would be to stand up here and just tell you what was going to be on the test and give you a test and see if you could just burp it back to me, right? Everybody would pass, everybody would be happy, I'd be a hero, right? What is my reputation in clinicals? You can be honest. Not good, right? He's an asshole, you know? I know what it is. I know what it is. But that's what I'm trying to do is my thinking is not to try to get you ready for this test. There's a test coming 2 years from now, and that's what I'm trying to get you ready for. Okay, so again, a little bit of a rabbit trail there. Electron binding energy, we talked about that. And we're going to talk about the significance of that here in a minute. Two things about electron binding energy is that if you have an atom with a big nucleus, it's kind of like having a big sun. If you have a big sun, it's kind of like having a big planet. What we say about big planets and gravitational pull. Larger gravitational pull, so they hold those planets, moons, or electrons into a tighter orbit, right? So bigger nucleus, higher gravitational pull, and we also talked about Mercury and it going around the sun really, really fast, right? It going around the sun really fast, and we talked about centrifugal and centripetal force. So those are the forces that hold Mercury into place, similar to how the electrons are held into place. That force that holds Mercury into place has to be very, very high, right? So the closer you get to the nucleus of the atom, the higher that binding energy is, okay? So that's a lot, right? We talked about a lot of stuff on Friday last week. So also, at the end of the class, I usually end every class with any questions. What does that mean?
Ask questions.
Any questions? Right. So, and y'all are good. You know, y'all give a lot of feedback. I love it. But anyway, that's your time to ask any questions if I didn't make something clear, and I do understand that, you know, sometimes I got to next class kind of dial everything in to make it more clear. But also, you know, if you have questions, I know, you know, X-ray techs tend to be introverts, so you don't really want to speak up in class. I get it. You know, room full of 33 people, I probably wouldn't ask questions either. But Canvas is open with questions that you can ask anonymously. Ask questions. You know, I would rather you go through Canvas than to email with questions, because chances are if you have a question, somebody else has the same question, and you know, everybody can review it. Maybe even open a discussion. So, with that in mind, any questions? Yeah.
Can you go over centrifugal versus centripetal again?
Yes. Okay, good. And all right, so what we're going to do today is we're going to go over the new material, and then I'm going to back up and I'm going to talk about the kind of the rabbit trails that went down, and that was one of them. Okay, so centrifugal versus centripetal force. So you have two forces that hold things, that hold things into orbit, right? So the centripetal force is kind of like the gravitational pull, okay? So that's what keeps the electrons from flying out, okay? But the gravitational pull is very high, especially when you get to the center, towards the center, innermost shells, towards the nucleus. So what you also have to have is centrifugal force that would keep it from flying outward, or I'm sorry, keep it from falling into the nucleus, right? So I talked about the bucket, right? Say, grab a bucket of water or whatever, and you spin it fast enough, then it stays in the bottom of the bucket, right? But if you slow down, then it falls. You are the nucleus in that analogy, and it falls and gets you wet or dirty, depending on if you got sand or whatever. So centrifugal force keeps it out of the nucleus, and centripetal force keeps it from flying away. Yeah. So you got to have them both, and essentially got to be the same, right? If one gets too high, then you got a problem. If one gets too low, you
So it's
also
like
got
a push and pull,
yeah,
equal push and pull.
right,
So would you think that centripetal is more gravitational
exactly.
and centrifugal? Or
Centrifugal. It's like the speed of
more
Mercury.
speed.
Yeah,
Yeah, okay.
yeah. I think you're right. I don't think the air is working down here. I turned it down to 68 and I don't feel it.
It's a little, it's a little.
Yeah, it could be because it could be because it's kind of cool outside. So any other questions? Okay, all right. Then we're going to talk about the atomic nomenclature, and then what I'm going to do is I'm going to bring up the review and kind of show you what I'm talking about. And I'll talk about the other little rabbit holes so that you just kind of understand, you know, my methodology. There is a method to the madness most of the time. No. All right, so atomic nomenclature, where we are right now is on page 43. So before we get there, if you flip back over to page 37, you see the elemental table. And that was Dmitri Mendeleev's contribution to kind of the atomic, development. So he identified, I think it was 54 different elements. We're up to 118 now. And some of those are man-made, and again, we're going to talk about the significance of that here in a bit. If you flip over to page 42, you can kind of see what I was just talking about, and something else that I had mentioned on Friday last week. So, so carbon, if you look at carbon and you just look at the diagram there, and we're going to talk a little bit more about it, it doesn't have just a whole lot of subatomic particles inside of the nucleus, right? So number of your protons, number of your electrons should match. If you have 5 protons, you should have 5 electrons. You have 6, you should have 6. So what you've got there is a couple of different things, and that is that the nucleus doesn't have a whole lot of particles in it, right? It's just got a few. So if you look over at the 3 columns next to it, you see it only has 2 shells. So it's got a K shell and an L shell. Remembering that the K shell is the innermost shell, and then it goes alphabetical order after that. So it only has 2, L shell has 4, and then the approximate binding energy is that gravitational pull, that's centripetal and centrifugal force, is holding those electrons into their orbit. So if you look at the K shell, KeV, what I want you to lock into your mind is KeV is the, essentially, it's the binding force of the electrons in those shells, but it's identical to KVP. Okay, so what is KVP? Kilovoltage peak, and we use that to make X-rays, right? So the higher the KVP, the faster the electrons go across the tube, and the higher the energy of the X-ray photon that we're going to create. So now that the interesting thing starts. So carbon, our atomic number is 6 on carbon. Our atomic mass is, it's higher than that. But if you look at barium, what's the atomic number on barium? It's a bottom number right across from where it says barium.
56?
56, right. So you've got another atom there that is has 9 times the mass, okay? And I know these aren't drawn to scale, but what do you see in the nucleus of the barium atom? Is it really bigger?
It just has
Just in
more
the-
protons and neutrons.
Has more protons and neutrons, and the electron cloud is tighter, right? So that's going to play a part here in a bit. You know, we're going to talk about that either today or next week. And then you get down to tungsten. Tungsten, the atomic number is 74, so it's about a little less than half again as high as what barium is. But if you look at the atom, what do you see? Almost identical in size, right? Yeah, so everything just got more compact. Everything got more compressed. Now, let's apply that to what we were talking about before the last test. You have a quantity of lead and you've got a quantity of aluminum. And they're identical in size. They look a lot alike, right? But which one's heavier? Lead. Well, what's the atomic number of aluminum? Flip back over to, I don't know how to search for this.
13.
It's 13, right. What's the atomic number of lead, which is Pb? Yeah, 82. Right? So what's the difference between those two, fundamentally? Nuclear weight, right? So you've got the same quantity in a measurable amount, but the weight of the two things are totally different. So, and I'm gonna tie that in eventually, but you know, I want you to be thinking not just that, you know, the nuclear size gets bigger, but maybe it doesn't get all that much bigger, but it gets more dense and the gravitational pull is greater, and therefore those electrons are held in a whole lot stronger. For example, if you look at the K-shell binding energy, inner shell binding energy of barium, what is it?
7.
That is tungsten.
37.
Yeah, it's 37. And then the tungsten, we're going to say 69. It's 69 and a half. They rounded it up for this, but on all tests, you're going to see tungsten inner shell binding energy is 69. Okay. So just kind of lock that in. You can even change it on your page if you want to. All right, so then we get to atomic nomenclature. We've got chemical symbol, and that is just those are the letters that identify the symbol. And it gets a little bit complicated when we have symbols that start, or elements that start with the same letter. Like hydrogen has 1 electron, 1 proton. Helium has 2 and 2. What do they both start with? H, right? So we can't really use H on both of them. So hydrogen is going to be H, helium is going to be He, right? So you've got to understand that it might stand for something, you know, maybe the Greek version or something like that. For example, tungsten. Where's tungsten on the other page? There it is. Yeah, tungsten is about 4/5 of the way down that chart, and it's a W, right? Because T was already used. So the chemical symbol are just the letters that represent the chemical, okay? And you're not going to have to memorize the elemental table. You know, we're just going to talk about a few things off of the elemental table. We're going to talk about the significance of those atoms as well, but you don't have to memorize all that. All right, so that's one thing. The other thing is, or another thing, is the atomic number. The atomic number is just the number of protons, okay, that identifies what the atom is. So hydrogen is always going to have 1, just 1, and only 1 proton, okay? If we get 2 protons, then what we've got is a change in the element. Now we've got helium, okay? So 1 proton means we've got hydrogen. 2 protons means we have helium. 3, you know, we've got something different. So that identifies what the number is. So the atomic number and the atomic symbol kind of go together. And again, you don't have to memorize all of that. Again, more penguins you don't need. But what you do need to know is the atomic number identifies what the atom is. You know, you change the atomic number and you change the atom, okay? You also need to know that in a electrically neutral atom, the number of positive charges, which are your protons are gonna equal the number of negative charges, which are your electrons, right? Protons, where they're gonna be found?
Nucleus.
All positive charges are gonna be in the nucleus, right? So, until we get to it, all negative charges are gonna be in the shells, right? So all of your electrons for now are in the shells. All protons are inside the nucleus. That's primarily what you need to know. What if you have too many protons? Or I'm sorry. Let's say you have more protons than you have electrons. What do you have? Positive charged particle called a ion, right? So if you knock electrons out, what do you have? Positive ion. What if you add electrons? You got a negative ion, right? So what if you knock a proton out? You got a different element, right? You got a different element. When are you ever going to knock a proton out? In a word, never, never. We're never going to knock protons out, right?
Well, isn't like alpha?
Okay, we're going to get there next week. And yes, that can happen. We're not going to do that.
Oh.
But we're going to get to alpha emission, beta emission. Yes, is the short answer. We're not going to do that, though. So everything that we do has to do with ionization, which is knocking out electrons, okay? But if you add electrons, you're also going to ionize as well. So the takeaway here is any dissimilarity between protons and electrons, and you've got a charged particle, which is a ion, right? Okay. All right. So the atomic number, beryllium is right there at the top, has 4 protons. The atomic number is determined by the number of protons, and that determines the element, right? So we have 4 protons. How many electrons should we have? 4. Otherwise, we have an ion, right? So atomic mass. All right. So we've got a different atomic mass than we have atomic number. So if we have a different atomic mass, what else can go inside of the nucleus? Neutrons, right? So if we have an atomic number of 4, and we've got an atomic mass of 9, what is it telling you? 5 neutrons, right? Okay, you got 5 neutrons. So number of naturally occurring isotopes. We're going to talk about isotopes here in a bit, and then we're going to talk about radioactive isotopes next week. So an isotope, just real quickly, is if you have 2 different beryllium molecules. Say we've got one and its atomic number is, because it's beryllium, 4, but its atomic mass is 8, let's say. Well, what does it say beryllium is? It's 9, right? So so you're not going to have this situation because it says naturally occurring isotopes. It's always going to be atomic mass of 9, but if you had one that had 8, that will be an isotope. What's the element? Still beryllium, because it has an atomic number of 4, right? Atomic number of positive charges equals the type of atom it is. So chemical symbol doesn't change, you know, it's still beryllium. But if you look at carbon, how many naturally occurring isotopes do you have? 3. So you could have 3 different elements of carbon, and you do. Some of them are radioactive, and they're inside of you right now. Okay, so you've got carbon, the atomic number is 6. So what does that mean? 6 protons, 6 positive charges, right? So, but it has 12, the atomic mass is 12. So, but it has 3 naturally occurring isotopes. So 12 is the average, right? You could have 10, 11, 12. So you've got 3 different naturally occurring isotopes of carbon, and it's probably something more like, well, I know carbon-14 is one, so it's probably 12, 13, 14. Okay, so we're going to talk about carbon-14 next week. So again, what we've got in that is we still have carbon in each one of those, but the atomic weight is a little bit different in each one of those. All right, so the elemental mass doesn't really matter, but notice if you look at K-shell binding energy, and again, we're on page 43, if you have K-shell binding energy and you put your hand on atomic number and K-shell binding energy, and you just kind of scroll down, what do you notice as the atomic number goes up?
The binding goes up.
Binding energy goes up on each one of those. So that once we get to tungsten, what do we have?
69.
69 and a half, right. We're just gonna say 69, it's just easier, okay? So, if you flip the page over, then essentially we've got 4 different things to consider in atomic nomenclature. And we just talked about one, and that is isotopes. When you have elements, two molecules of the same element, but they're not exactly the same. You know, they're the same element, so we've got carbon 12 and we've got carbon 14. Then what we've got there is they're still both carbon, it's just carbon 12 has a little bit lower weight than carbon 14 does for a period of time anyway. So you got different isotopes. Isotope is something that, it's an element that has the same atomic number, but it has a different number of neutrons. So it's the same number of protons, because it's the same atomic number, different number of neutrons. Okay, so the elemental weight might be a little bit different, but it's still, in both cases, it's still carbon. So that's an isotope. So same number of protons, different number of neutrons, and we'll talk a little bit more about that again next week. So isobar has the same atomic mass, but a different atomic number. So if it has, if we're going to round off our mass as being 1, and we have, let's go back to our chart. No, they couldn't have done this easy. They don't have 2 that are side by side. So if we go to, and they use atomic mass. Okay. All right. So if we had, well, let's do this. This is hypothetical. It's completely hypothetical, not realistic at all. Okay. So what if we had carbon and its atomic mass is 12? Okay. Its atomic number is 6, right? So just under that you got oxygen, right? So what if we had oxygen and its atomic mass was also 12? Yeah, also 12. Would it be the same? No. So we got the same atomic mass, but we got a different element altogether. So compared to isotope, you know, if you want to forget one of those 2, forget isobar. Okay, remember isotope. Isobar doesn't really have a big place in what we do, even in nuclear medicine, just not a big place. So an isotone is the same number of neutrons and a different number of protons. And again, it just doesn't matter all that much. And an isomer is basically this, you know, they may exist on different energy levels, but they are the same all the way across the board. They have the same atomic number, same atomic mass, so it's the same element, same number of protons, same element. They're just twins, essentially, right? So that's those 4. And the last thing that we're going to talk about before we take a look at the review is combination of atoms. And we talked a little bit about this a few days ago. And we have essentially 2 different ways that we combine atoms. Okay, so going back to Dalton's hooks and eyes, we have 2 different ways that we combine atoms. We talked about covalent bonding in water. I want to show you a video, by the way. We talked about covalent bonding in water. Do you ever see water being created? You sure?
You said last week, yes.
Hmm?
Yes.
Yes. When do you see it? You're right, you do.
Rocket ship.
Bingo. Space shuttle specifically. Let's see. I think nobody has ever brought up YouTube down here. It says try searching to get stuff. What? Okay, let's see. Let me see if this is. There we go. So there used to be this TV station, and it was glorious. It was called MTV, and it actually, the M stood for music. I think it still exists. They don't play music anymore. You know, it's awful. But anyway, this was the kind of the opening scene, you know, as their propaganda commercial. What it is the space shuttle getting ready to take off. And what you see on space shuttle, you see this picture over here. Can you see it? Okay, so what you've got in a space shuttle is you've got three different things essentially. Okay, so these white things on the outside are what they refer to as solid rocket boosters, and they're enormous. They're huge. But compared to that big orange thing, they're pretty small. So what's in that orange thing is it's divided, and in one side you've got oxygen, liquid oxygen. If you didn't know, you can liquefy oxygen. You can liquefy helium. You can liquefy oxygen and hydrogen, and what you've got in there is hydrogen and oxygen liquefied. All right, so you've got the components of water in this big orange thing. And what has to happen, you know, believe it or not, oxygen can be pretty unstable. I used to be an aircraft mechanic in the Air Force. I don't know if I've ever told y'all that, but how we pressurize the airplane is, and I've worked on an enormous airplane. They took two of the airplanes and they gutted the inside of the airplane so that these rocket boosters would fit inside of them. So we had two airplanes. Most of the airplanes, you know, it's like you take a 747, the size of a 747, and you add about 75 more seats just in front of the tail, and that's what you call a C5. So in order to get these rocket boosters inside of the C5, they had to take those seats out, right? And that was just weird to see. You walk into the cargo bay and you could see all the way to the, you know, to the top of the fuselage. But at any rate, these things are enormous. That thing is even bigger. So in order to make water, what we have to have is a very violent, explosive reaction. When we had we pressurized the airplane, we'd carry liquid oxygen in the airplane. So we'd have to fill the thing up. Sometimes it would get contaminated, the oxygen would get contaminated, we'd have to drain it out. And it's dangerous. If the liquid oxygen touches oil, it can be explosive. So if you're ever at the airport and you're looking where the airplanes are parked, they're not parked on asphalt, they're parked on concrete. And the reason for that is because your airplane that you're going to get on is pressurized with liquid oxygen. So they can take all the oxygen in this room, and if they cool it down enough, it comes down to about this, you know, I'm guessing here, maybe the size of, you know, one sip of water out of your cup, very small, right? So we take these spheres and fill them up with liquid oxygen, bleed some of that off to pressurize the airplane. So this is carrying a whole lot of oxygen, right? So just combining the oxygen and the hydrogen is not enough. It needs a spark. And so when we watch MTV, this is what you would see. You got the spark. And I'm not saying all of that is water vapor, but a lot of that is, okay? So you've seen water being created. You just didn't know it. You thought, well, that's a rocket. It's blowing off a lot of smoke. Yeah, it is from the solid rocket boosters. But a lot of that, if you were to walk through that cloud, you would come out looking like you just climbed out of a shower. That's a lot of water. Okay, so what you're witnessing there is covalent bonding. So covalent bonding is very difficult to create. You can't do it. And you can create water, but you're going to need some specialized equipment and some specialized material. You're going to need liquid oxygen and liquid hydrogen, a spark, and then you better get out of the way, right? So this is a controlled explosion is all this is. A sustained and controlled explosion. Covalent bonding, hard to create, hard to break apart, often very violent in its creation. So the purpose for covalent bonding is what I drew up here before, and that was to make the element or the compound as stable as possible. Well, how do you get to stability? There's two things. You want as many protons as you have electrons, but that's the minimum. That doesn't really make it stable, it just makes it electrically neutral. The most stable is if it has 8 in the outer shell, right? So that's what you're seeing here, is two elements coming together, one has two parts, or two parts one thing and one part the other, to create covalent bonding to make something extremely stable. Water. What you have with ionic bonding is a little bit different. It's a lot different. It's easy to create and easy to break apart. So we talked about this a little bit. How do you get ionized? You specifically. I'm not talking about in an X-ray room. I'm talking about wintertime. What happens? Static electricity. Right. You become ionic, right? And maybe not in the same way that an X-ray beam will ionize you, but you're an ion. You're just a big walking ion. Is it hard to get rid of all those those extra electrons? No. Just find somebody you don't like and touch them, right? You zap them. You're a miniature stun gun at that point. So ionic bonding, what you have is one atom gives up an electron. So it gives an electron to something else. It becomes an ion. So if it gives an electron to something, what does that thing become? It's got an extra electron, so it's a negative ion, right? But if I gave up an electron, what do I become? Positive. So opposites attract, and that's ionic bonding. So in both cases, what you'll see in some of your reviews, tests, things like that, is that it'll make a distinction between ionic bonding and covalent bonding, and it might say something to the effect that ionic bonding is sharing of electrons. Is that true? Yeah, it is. One gives up, one takes, opposites attract, you've got an ionic bond. But covalent bonding is also sharing of electrons, but it's sharing of electrons to do something specific, and that is to get 8 in the outer shell. Okay, big difference between the two. Violent, very strong bonds, covalent bonding, excuse me, ionic bondings, it doesn't take an explosion to make ionic bond. Okay, so that's as far as we're going into the lecture today. Any questions on that before we take a look at this and try to look at the practical application of how to use these? Yeah, what you got?
So when we were going over isotopes and we talked about all 4 of the things, do we only need to know isotope essentially?
Isotope and
Right
and isomer, but isotope primarily because and we'll talk about isotopes specifically in context of radioactive isotopes. Carbon-14 is it's a naturally occurring radioisotope that you've got in your body all the time. So that's the most important of the 4, yeah.
So an isobar is literally just different elements that have the same atomic mass?
Yeah.
All right.
Anything else? Okay, so how to study, a few things. First, let me see if this is in here. No, it's not. So let me go back out to positioning. So, you know, I'll have students ask sometimes, how do I study for this? And, you know, the short answer is, I don't really know, you know, because, you know, your learning style is going to be different than mine. You know, I'm a visual person. I have to visually disassemble something and put it back together to make sense of it, right? Some people are auditory, some people are visual, some people are tactile, they have to touch it. You know, somebody who's tactile may struggle in class and they may be in clinicals the best student we have. So, you know, your learning style, my learning style are going to be a little bit different. There's, you know, in your positioning class, not the lab portion, but the positioning class, if you click on that, it should take you to a link that you can kind of get some tips and hints on how it will help you to study, okay? But how you interpret my reviews is kind of what we're going to talk about. So you got a couple of things already in the 2309, you know, the physics Canvas module, or Canvas shell rather. One is final reviews already up. Okay, so I wouldn't recommend spending any time on the final review just yet. After we get through the atomic structure, then you might start just kind of glancing over it a little bit at a time. And what you'll find in the physics review is that I've taken everything that the ARRT says that you need to know to pass this portion of the registry. And I've given you kind of topics and questions coming at you from a lot of different directions. So as you read through it, what you'll see is some redundancy built into that, because the registry may ask you the same question from different directions, right? So I don't recommend spending any time with that until about mid-semester, and once you do, maybe just start kind of perusing it a little bit. Towards the end of the semester, really start studying it, okay? So nothing on the final, it's not in the final review. But same thing also though with the individual tests. So I need to go in, I need to reload these, because if you open some of these, it does, like this one says chapter 3, but some of the other ones don't. So you got a little bit in chapter 52 on this, and some of the things in here are pretty straightforward, and then some of them require a little deeper thought, right? You know, so what does the Bohr model resemble as a solar system? You know, so some of these things are pretty cut and dry, but some of them require you to think a little bit deeper, right? So I feel like I'm echoey, like so maybe the speakers are on, I don't know. But anyway, I still hear it. So anyway, reading through this chapter here, you know, it's trying to get you to think a little bit deeper. So what's the significance of the Bohr model as we know it? Well, what do I say about X-ray creation? What's the main thing that we create? Is heat, right? So why do we create so few X-ray photons? What do we have to have in order to create the X-ray photons? There's two ways we create X-rays. Brims and characteristics, right. So how big is an electron? Very small. It's so small we don't even give it an elemental mass. So it's so small that it almost doesn't exist, right? And what are we shooting that thing at? Two things. Either another electron, which is also so small it almost doesn't exist, or the bigger thing, which is the nucleus of the atom, which is so small we can't see it, right? Where is most of the mass in the atom? The nucleus. What is the atom mostly made of?
Empty space.
Empty space, right. So again, what is the significance of, you know, my little lecture on Jupiter being the vacuum cleaner of the solar system, and comets having such a elliptical orbit?
Gravitational pull?
Gravitational pull, exactly. It's a gravitational pull, but at the same time, it's you know, it's the gravitational pull specifically in the comets that are still existing of the sun. That comet has to get close enough to the nucleus of the atom to be kind of slingshot around, right? Then it goes off in the distance, gravitational pull's still there, eventually it slows down and comes back, right? So what if it was at a greater distance from the nucleus? It's just going to go off into space, right? So what is that comet kind of sort of a picture of? We shoot an electron into the atom, it gets close enough to the nucleus, and it does what? Shoots away because of the gravitational pull of the nucleus. It's going to grab it and it's going to change directions. As it changes direction, what happens to the kinetic energy? Tying this back to the second test. It slows down. We lose kinetic energy. But according to the law of conservation of energy, it slows down, but it's got to go somewhere. So where does it go? X-ray. Right. But again, what we've got in that, drag that one up, is that we've got a nucleus that is that big, and we're going to be shooting a stream of electrons from 10 miles that way, trying to hit that or get close to that. What are the chances that's going to happen? Very slim. Are some of them going to get close? Yeah. So what we're going to have is electrons passing at various distances away from the nucleus. These are all brims, right? These are all brims passing at various distances. The further away from the nucleus we get, then comparatively speaking in a word, how much energy are we going to lose? More or less? Less. We're going to lose less the further we get away from the nucleus of that, right? So what's that going to do? If we lose little energy, what is that going to do to our X-ray photon? Are we going to have a high energy X-ray photon or low energy X-ray photon? Low, right. So what did Rollins introduce to try to get rid of those low energy X-ray photons that aren't going to do anything except for add to patient dose? Filtration, right. Okay, so this is all kind of tying together now, right? All right, so what's the second way that we have to, the second way that we create X-rays? Characteristic, right. So our characteristic, we've got, I got to condense my atom here. So we've got electrons in shells, and the electron's so small that I'm not even going to try to draw one. I'm still shooting from 10 miles away with something that's so small it almost doesn't exist, and I'm trying to hit something that's blasting around this nucleus of the atom, and it's also so small it almost doesn't exist. What are the odds that that happens? Greater or lower than the brims? Lower, right, lower. But here's the rub. Flipping back over to page 42, what do we use for our target? Tungsten, right. So if you're looking at tungsten, now we're looking at the approximate binding energy over on the right-hand side. What's the binding energy of the inner shell electron for a tungsten atom? 69 kVp, right, or KeV. KeV equals kVp, right. So let's say you're shooting a hand X-ray. Anybody shot a hand yet? Yeah, okay. So remember what kVp you used?
55.
Okay, I'm getting all over the place, but so I got 55. I've got, what'd you say?
I said 55.
55.
That's
Somewhere around 70. Really? I don't disagree with using 70. We'll get to that next semester. But 40. Ooh, I disagree with that. All right. So if KVP equals KEV, okay? You know, two sides of the same coin. This is held into place with 69 kVp, or no it isn't, keV worth of energy, and I send that 55 kVp X-ray photon, or electron in. Is this gonna have, again, going back to the last chapter, enough momentum to eject that? No, it's gonna go doink, and it's still floating around out here. Okay, so what do I have to do to create an X-ray photon, characteristic X-ray photon in tungsten atom?
Have higher KVP.
I have higher KVP. So, in your 55 KVP X-ray beam, what were 100% of your X-ray photons created by? Okay, so why did I bring all this other stuff in? Try to we're looking at something we can't see. Can you see a solar system? Yeah. Stars were gorgeous last night. I live in the sticks, and there's less light pollution. If you live in Tyler, get out of town. Get out of town. Look at the sky. It's amazing. If I go to the backside of my property, spread a blanket, you can lay down. You can actually see satellites and the space station fly over. Yeah, it's really cool. It really is. If you really want to see the stars, Big Ben. Thank you. Yeah, Big Ben is amazing. And daytime is amazing because it's just beautiful. And then nighttime, you're like, wow, I didn't know those existed. It's phenomenal. As gorgeous as my night sky is, it compares not at all to Big Ben. Big Ben has near zero light pollution. So anyway, I want to expand on this a little bit. Look at the approximate binding energies of, again, tungsten. So inner shell, K shell is 70. Okay, so why do I make a big deal out of the proximity to the nucleus of the atom? Well, what's the next one out? Binding energy. 12. Okay. Can you get a 12 kVp X-ray photon off of that 55 off of the K shell, or the L shell rather? Do I have enough momentum at 55 kVp to eject that? Yeah. I can eject that one, and I can make an X-ray photon that's 12 kVp. And my next question is, so? What are you going to do with a 12 kVp X-ray photon? Nothing. Okay. Mercury. All right. Mars. So what's the X-ray we're going to get off of Earth? 2.8. Useless, right? So the significance of using the solar system as a model. Mercury orbits fast, has a great gravitational pull because it's close to the sun. Inner shell electrons very well bound because it's close to the nucleus. Big nucleus, or heavy nucleus anyway. Big nucleus, higher binding energy, closer to the nucleus, higher binding energy. These are the ones we're going to concentrate on. Do you get a characteristic X-ray photon out here? Yeah, but it's useless, so we don't count it. You get a character. We actually have maybe 15 different characteristic combinations we can have. We'll go through that later in the semester. Some of them are good, but if we're just talking about individual shells, nothing but the K shell matters. We have to have K shell interaction in order for it to matter. Okay? I think we're probably over time at this point. So how do you use the reviews? Oh, if it's just something like a simple definition, that's all you got to have. But if it's something deeper than that, think deeper than that, right? So why do we use tungsten? Because it's got a big nucleus. What's the significance of big nucleus? Better gravitational pull. We can get better brims off of it. Okay, so what is the significance of the binding energy? Well, if we have a high binding energy, we can get useful characteristic off of it. Right, so it's a little deeper understanding, deeper deeper thought process than, just superficial. Any questions?